Hello and welcome to this presentation on DirectX 11 rendering. So far we've created a basic Windows program and we've created certain DirectX interfaces to get us access to the back buffer and a drawing surface, and now finally it's actually time for us to draw some items on that surface. Before we get to the drawing, we'll do a little background. One of the first things that we want to refer to is coordinate systems. Our objects are going to be three-dimensional, and we have at least a couple different choices of coordinate systems. One way of categorizing coordinate systems is based on whether they're left-handed or right-handed coordinate system. And the way you can tell whether a coordinate system is left-handed or right-handed is by taking in the case of left-handed, take your left hand, take the tips of your fingers of your left hand and point them down the x-axis. Then curl those fingertips up to the y-axis, and your thumb will tend to point in the positive z direction. If you do that with your left hand, you see that if x is to the right and y is up, then z goes into the screen or away from you. If you do this with your right hand on a right-handed coordinate system, it'll be the opposite. In our case, in DirectX, we are having and using a left-handed coordinate system. Although you can change this, we'll be using a left-handed coordinate system. I always find it maybe a little easier to think about if positive z is going into the screen or forward from the camera. Some of you may know that most of the three-dimensional objects that you see in computer graphics and in computer games are made up of polygons. In particular, triangles are the most common type of shape for these polygons. At the corner of each triangle or polygon is what's referred to as a vertex. So in this pyramid here we can only see 4 vertices. It looks like there's probably a 5th one in the background that we can't see. And each of those vertices makes up a face or a polygon or a triangle. A triangle will have 3 vertices. At the vertices, we need to describe the data necessary for that vertex. And there's at least 4 different pieces of information that we'll use this session. To begin with, we'll keep it simple and only use 2 of these, but the 4 pieces of information that are most commonly used are the position of the vertex, x, y, z, the normal of the vertex, and a normal is a direction vector perpendicular to the surface at that point. And normals are commonly used for lighting calculations, sometimes for physics calculations as well, but very commonly used for lighting calculations. A vertex can also have a color made up of 4 components: red, green, blue, and an alpha channel for transparency. And a vertex can also have a texture coordinate, and these are often 2D coordinate systems that look up into a texture map or an image. We often use the letters U and V for those texture coordinates, although if we use a particular data type in a shader language or in C++, sometimes it'll be an XY value because that's the way the 2D vector is defined, with an XY name instead of U and V. A concept comes up here with respect to what we call vertex shearing. So here we see that we have at least 2 faces. I'll put a 1 here and a 2 here. close enough. And you can see that face 1 and face 2 share these two vertices. And the question is, do we want to share vertices, or do we want to have each triangle have its own set of 3 vertices? And there are advantages and disadvantages to both schemes. The obvious advantage of having shared vertices is if you've got a lot of adjacent triangles, then you'll end up having less vertices. So that's less information to send across the bus to the GPU and less information to process. So this is a little more efficient. The disadvantage of having shared vertices is that the normal for this face, number 2, should be different from the normal face 1. They have different orientations. With shared vertices, that can be challenging to implement, and really impossible to implement, because you only have one normal per vertex. So which one do you use? Do you use the one for face 1? Do you use the one for face 2? Do you average them? That can be a potential problem. So if normals and lighting calculations are very important to you, you may not want to have what we call shared vertices. You may want each triangle to have its own vertex. We're not going to use normals yet. We may have them in our code, but just not use them yet. Our polygons will be shaded or colored based on the color information that's supplied for each vertex. So we could say, how many vertices do you need for this pyramid? And the minimum number are 4 on the bottom, 1 in the back that you can't see, and then the 5th one up top. That's the minimum number of vertices that you need. But if we count the number of faces as 1, 2, and then 3, 4 in the back, and then multiply 4 faces times 3, we get 12 vertices if we don't want to have shared vertices. Another interesting question is, what do you do about the bottom of the pyramid? Do you want to have faces on the bottom of the pyramid? Well, if it's in a scene as a pyramid, then the bottom of it may be stuck into the ground, and the user may never see it. So there really isn't a need to have bottom faces or close off that pyramid shape. If that pyramid shape is going to be flying through the air, then yeah, we may want to close off the bottom. In that case, the bottom of this 4-sided pyramid is going to be a square, and we need to represent that square as 2 we can represent that square that would be the bottom as 2 separate polygons, triangles. So in that case, we'd have 1, 2, 3, 4 faces making up the top part of the pyramid, and then 2 more faces on the bottom, so that would be a total of 6 faces. And if we don't want to have shared vertices, then 6 times 3 would be 18 vertices. So the question of how many vertices are needed depends on whether you want to share or not, and the question of how many faces or triangles are needed depending on whether we need to close up the bottom of it or not. So the answer to these questions are really, it depends. Once we get the object in our scene, we're going to need to do some basic transformations. And if you've taken the 3D math for game programming, you may have seen some of these transformations. Some of them may be new to you. In the transformation category, sometimes I like to break these up into 3 major categories, and they are what I call world transformations, the view transformation, and the projection transformation. In the world, we can take our object. Here we have the famous Utah teapot, and we can take this object and we can rotate it In this case, they're rotating it 90 degrees about the y-axis, so the green arrow represents the y-axis here. And they're rotating that teapot 90 degrees about the y-axis. So this is a rotation transformation. Another common transformation is translation. So after the rotation here, they've done a translation down the x-axis. And so this is a translation transformation. Not shown in this diagram is another common one is the scale transformation, where we can make objects larger and smaller. And we can break up scaling into two further types. One is referred to as uniform scaling, where the object increases or decreases in size in all three directions equally. We can also do non-uniform scaling, where we can increase or decrease, stretch or shrink an object unequally in the three directions. So for example, if we were to take this teapot and use scaling factors of 1 in the y direction and 1 in the z direction, but 2 in the x direction, when you scale by 1 it doesn't change. When you scale by 2 it makes it twice as big. So if we made it twice as big in just the x direction, it would be like taking that teapot and pulling it, stretching it in both the positive and the x direction. So you can get different effects. For example, if you took a sphere and you stretch it in just the x direction, then it becomes an ellipsoid. And if you take a cylinder and you squish it in one direction, you can make it flat into a disc type shape. So there's a lot of different effects that you can do with scaling to make things into certain shapes. If we take our pyramid and scale it in the y direction, then it can become a very thin, pointy, tall type shape. If we take boxes and scale them non-uniformly, then they become rectangular shaped boxes rather than square or cube shaped boxes. So those are the three basic types of transformations for what we call world transforms, or transforming objects within the scene. Something to keep in mind is that these matrices these transformations are stored in 4x4 matrices. So three-dimensional transformations are commonly stored in 4x4 matrices for computer graphics. And we'll go over some more in a separate math presentation, but I want to make this important point. These transformations can be combined by multiplying those 4x4 matrices. A key thing to point out, though, is that in linear algebra, when you multiply matrices, that matrix multiplication is not commutative. What that means is that A times B is not equal to B times A if A and B are matrices, and that's not necessarily the case. And we can see this here. In this image at the top, they have two sets of transformations. In the top view, they rotate around the y-axis 90 degrees and then translate down the x-axis. So if we take the rotation matrix R and multiply that by the translation matrix, we can get sometimes they use the letter C for a composite or combined matrix. And so that letter C, that matrix C, if we apply that to all the vertices of this teapot, we'll jump from this step all the way to this step because we combined the two transformations in a single matrix, and by multiplying them together. And notice the order was rotation first and then translation. In the second image below, the order was a little bit different. We did translation first and then rotation, so that the object was translated down the x-axis first and then from this point it was rotated about the y-axis to end up in this configuration here. So in this case we did the translation first and the rotation second, and we get a different orientation, location and orientation for the teapot than we did here. And this is a key thing to keep in mind, is that the order in which you do these transformations is important, because matrix multiplication is not commutative. These next two categories of transformations, the view and the projection, have to do with the camera and our screen that we're going to view the scene on. For the view transformation, we won't get into the math of it, but we take information like the position of the camera, where's the camera located in our scene, what is the orientation of the camera, and we typically define that orientation as the look at. So what point are we looking at in our scene, and what we call an up direction or an up vector, which way is up. So if you imagine the camera tilting from side to side, or rolling or banking like an aircraft wings, you can imagine the camera's up vector changing. The look at is fairly simple, that's what we're pointing at or looking at, and then the position is also fairly straightforward. Another piece of information that we have for our camera is called FOV, or field of view. And the field of view is generally one of these two angles. So sometimes they define the field of view as the vertical angle in our viewing shape. Sometimes they define the field of view as the vertical angle in our shape. And this shape, this pyramid shape that's made from this view information, they have a funny name for it. They call it a frustum. So they call this the viewing frustum. And generally objects that fit within that pyramid shape, or that frustum, will be rendered, and objects that don't fit or outside will not be rendered. And in some cases you'll have polygons that will be clipped or modified because they intersect the edges of the frustum. In this case we'll see part of an object and other parts of it will be clipped. So it's really useful in our games to define variables for a camera's position, a camera's look at direction, up direction, and the field of view, and we may want to change this. The other, and again, this information falls within what I refer to as the view transformation, and it's also stored as a 4x4 matrix. Finally, we'll look at the projection transformation, which takes in the screen width and height and an aspect ratio and some other information about the limits of the depth, what they call the near and far clipping planes, and we create a projection transformation which takes objects and projects them onto the screen. The aspect ratio is typically the height of the screen divided by the width of the screen. And again, because all of these transformations, the world, the view, and the projection transformation, are stored as 4x4 matrices, once we get a combined world transformation, we can multiply that times the view transformation and multiply that times the projection transformation and transform our world points into screen points with a single multiply the vertex XYZ position times this combined WVP worldview projection transformation matrix. So how do we create, in DirectX, how do we create polygons? And if you think back to elementary school, you might have done little puzzles, little drawings they call dot to dots or connect the dots, and it's really similar to what we'll do here, except we'll be doing it in 3 dimensions. So let's take a look at a simple square here. So we've got a pretty simple square, and we're going to divide it up into 2 polygons. And it looks like this is the origin. It has coordinates 0, 0, 0. And this point here has coordinates 10, 0, 0. So it looks like this direction must be positive x. This one is 0, 10, 0. So it looks like this direction must be positive y. And we know that for a left-handed coordinate system, positive z would be into the page or into the screen here. So the coordinate here is 0, 0, 0. The coordinate here is 10, 0, 0. We go up 10, 10, 0, and 0, 10, 0. And so what we do then is define what's called a vertex buffer, which is an array or a list of vertex information, x, y, z. As we'll see in our code, we'll actually add color for each vertex, but for now we're just going to be concerned with the x, y, z. So we can see that the first vertex here has an index of 0. The second vertex here has an index of 1. The third one here has an index of 2. And this one has an index of 3. Okay, so if we call this, if we say that this is face A, and we say that this is face B, then in order to connect the dots for face A, we need the indices 0, 1, and 2. And that's what you're seeing here in what's called the index buffer. So the index buffer is how we connect the dots. And in our case, we're drawing triangles, so the index buffer will always have a number of indices in them that's evenly divisible by 3, because we're drawing triangles. So the first 3 values in the index buffer are for face A, and then the next 3 values in the index buffer are for face B. You see that we're drawing 3, 2, 1. So there's something else important that we need to discuss, and it's referred to as winding order. The winding order of a polygon is either clockwise or counterclockwise, depending on how it's seen from the camera. So what does this mean? For face A, if we specify in the index buffer 0, 1, 2, we're going from 0 to 1 to 2. And this is going to produce for us a winding order that is counterclockwise. So we'll say CCW. So it's a counterclockwise winding order. For face B, they've listed it here in the diagram as 3, 2, 1. 3, 2, 1. So this is also a counterclockwise winding order. So it's important to know when you create your polygons, and it should be consistent with the winding order. Why? Because if the camera looks at a polygon from the other side, then the winding order will be reversed. And one common technique to improve the performance is to cull or simply not process objects that don't match the winding order. Why is that? If you can imagine an object that's closed, like a closed pyramid or a closed sphere, we don't want to see objects that are on the other side. We only want to see the objects that are on the outside facing us. Objects that are on the other side facing away from us, we don't want to see them because they'll be blocked by objects on the outside that are facing us. And so it's very common to set up a winding order and set up a culling so that we don't see objects that are facing away from us. Now we can change this behavior, and we probably want to do that in the case of drawing just a single rectangle like this, because we may want to see it from both sides. In this case, we can disable the culling based on the winding order. Something you need to be aware of, and it can be a cause of some frustration because you can be drawing everything properly, but then your triangles are not seen on the screen because they're culled, because they have a winding order that's causing them to be rejected or culled from the rendering process. So it's something you need to be aware of. The next step in our process is to do the rendering is to actually we have to create a shader program. In this case it's going to be fairly small, but we have to create two functions in high-level shader language. The one function is referred to as a vertex shader, and we can call it a program or a function. Essentially it's a piece of code that's going to get called for every vertex. So as part of the rendering pipeline, we have a vertex shader that's going to get called for every vertex. And typically in our case, what we're going to do in the vertex shader is to transform the vertex from world coordinates to screen local coordinates. And we do that by multiplying it by the world matrix, multiplying it by the view matrix, and multiplying it by the projection matrix. Another step that we need is a pixel shader, and as a polygon gets converted to pixels, every pixel that's produced, I think they're calling it the fragment shader here in this diagram, every pixel that's produced is going to invoke the pixel shader program, or the pixel shader function. And so the job of the pixel shader is to figure out what color that pixel should be. Something that's done in these shaders and part of this pipeline is what's called interpolation, or lerp. So they use this funny term called lerp for linear interpolation. And what lerp does is it interpolates values along lines from one value to another. So in the case of our vertex color, the red component will be interpolated from one end to the other. The green component will be interpolated, the blue component will be interpolated, the alpha component will be interpolated. And so we can just use that interpolated color. So our pixel shader might be extremely simple. We could just use that interpolated color and have the color shaded across the face of the polygon. Other possibilities are that we could do lighting calculations, or we could do texture coordinate lookups, and we'll see those in future work in this class. As part of the creating the shader programs, we have to go through steps to compile and load the shader program. So the shader program is different ways of doing it, but the way we'll look at today is we can write the shader program in a separate file and then load that file in our C++ program and compile it, and then take that compiled shader program and set it in the appropriate stage of the pipeline. In order to do that, we need to add some additional header files and library files. In particular, we need to add d3d shader and compiler.h and d3d compiler.lib. So let's go through the process of seeing if we can make all the necessary changes to see a simple triangle. Here is our pretty much our DirectX11 initialization program from last time, and you see it just produces a screen that, where we're putting a custom color in the back buffer and displaying the frame rate in the title bar. So again, one of the first things that we need to do is to add some include files. And in particular, in the header file, we need to add D3D shader, and in the CPP file we need to add the D3D compiler.h. We also need to add in our linker inputs we need to add D3D11.lib and D3D compiler.lib. One of our next steps that we need to do is in the header file, and you may want to create a separate module for this. We'll look at that next week. But we're going to create a structure to define our DirectX vertex. And in order to do that, we need to add some code from this math helper that comes with the we can find in the Luna textbook, and we'll also add in our shader. So we're adding in some additional files to the program. The shader will have to write. The math helper.h and the math helper.cpp, I believe they come from the Luna textbook. So we'll add those to our project. And notice that the shader.txt doesn't get added in the source files section. It's just really a data file. We'll take a look more at this later. The math helper.h and the math helper.cpp get added to the header file and the source files section. We'll go ahead and compile the math helper and make sure it builds okay. And we'll just briefly run through what's in here. It has definitions for some random functions, min and max, lerp, clamp, some angle, infinity, and pi. So we may need some of these. The other thing that it does is it includes DirectX math.h, which comes from Microsoft, and we'll have a separate presentation on this in the future. Also, in the mathhelper.cpp, you can see the definitions for pi and some of the other functions that we might find useful. So then we will include mathhelper.h, and then now we should have definition for a 3D position and a 4-dimensional color. All right, the next step then is to create in our application, we want to create definitions for some new variables. And these new variables are for a pointer to VB, so this is a DirectX11 buffer, and the VB is vertex buffer, and the IB is index buffer, and the input layout is going to tell DirectX how those buffers are laid out. Are they XYZ then color, or are they color then XYZ? DirectX11 needs to know what information is in them and what order that information comes in. And then we're also going to create interfaces for our vertex and pixel shader, and we're going to create interface for a constant buffer, which allows us to transfer information from our C++ program to the shader program, and that information is going to include the world view and projection matrices that we talked about. So now one of the next steps is to actually do some of this initialization, add some of this additional initialization. And so we're going to create a couple of new functions. In addition to initializing 3D, we're going to create a function to initialize geometry, initialize shaders, and just be able to get us the aspect ratio. So if we look at the initialization of the geometry first, we'll start out by creating just 3 vertices in an array, and the vertices have a position, so 0, 0, 0, 10, 0, 0, so this is going out 10 on the x-axis, and then 10, 10, 0, so this is going out 10 on the x-axis and up 10 on the y-axis. And the color of all these are going to be RGBA, so all of these colors are red. So we're just creating one simple triangle, and we're going to use indices 0, 1, 2 as for our index list that will ultimately make up our index buffer. So now the code to create the vertex in the index buffer requires that we fill in these descriptor information. So we have a buffer descriptor. We zero out the memory of this buffer descriptor, and we tell Direct3D some information about it. In particular, it's going to be dynamic. We might want to change it, and the size of that buffer is going to be the size of our structure in bytes times the number of vertices here. We're going to bind this buffer as a vertex buffer, and we're going to give the CPU access to write to it so that we can change it. We have to declare this sub-resource data and set the system memory of the sub-resource data to our vertex list variable, and then we can, through the Direct3D device, create that vertex buffer. The next step here is to create an index buffer. It has a very similar process. The size of it is different because every piece of data in the index buffer is just a number or an unsigned integer. And we have, again, we have 3 indices. We're binding it as an index buffer, giving it write access, setting the sub-resource data, and then creating the index buffer. The next step is we're going to create a constant buffer. And in this case, we're binding it as a constant buffer, and we're setting the size of it to a matrix. So a matrix is a 4x4 array of floats. So it's going to be 16 times 4 bytes for each float, so it's going to be 64 bytes. In this case, we're going to multiply in our C++ code the world view and projection matrices together, so we just need to send over one matrix. In some cases, we may need to send more than one piece of data, in which case the size will be larger. And here we create this constant buffer. The next step is to initialize the shaders. So in this case, we create these pointers with an odd name. They are D3D blobs. So a blob in programming in some database areas is short for binary large object. So in this case, our programs are being compiled from files and compiled into what we call blobs. So here I've put the shader.txt in the source folder. So you can see in the source folder we've got the shader.txt, and I'm compiling a vertex shader. That's the name of the entry point. So in the high-level shader language, I've got vertex shader here, and I'm using vertex shader model 5.0, and that's not all that critical. That's one of the later ones, but it's not all that critical at this point. The compiled program will end up in this blob, and if there are any error messages, they'll end up in this blob. If this fails, and there are error messages in our shader language, this bit of code will get those error messages and display them in a message box. And that's a useful thing to have. We do something very similar for the pixel shader. Notice that in our shader program we have a vertex shader and we have a pixel shader as 2 separate functions. And so we do the same thing for the pixel shader using pixel shader 5.0. We should have the error messages here too. The next thing is we need to get the data out of those blobs and set those in our vertex and pixel shader objects if they compile successfully. So that's what these 2 lines do. And then we tell the device context to use those shaders. And this brings up an interesting idea in that if you wanted to have slightly different rendering effects, you could create more than one pixel shader and draw one object with pixel shader 1 and draw another object with pixel shader 2, and they would have slightly different rendering effects for them. The next step here, because we need some of the information from the shaders, we put this input layout step here with the shader code. And what we do is we declare an array of vertex descriptors, or vertex element descriptors. And so what this has to do is these pieces of data in the vertex element descriptors have to match our definition for a vertex. So the first piece of information in our vertex is a 3D position. So there are 3 floats for XYZ position. And the second piece of information is a 4 float color. So in our descriptor we say that the first thing is position. It's made up of, it's kind of weird, they're using RGB, but essentially it's just one 32-bit float, another 32-bit float, another 32-bit float. So 3 floats, and there's one of those for each vertex. The next, and it starts at offset 0. So that's the first thing. The next one is for color, and you see here that it's using 4 32-bit floats for RGBA, and this says to align it so that it's packed right after the position. So we could also put in I believe a value of 12 here, because there's 3 XYZ, 3 times 4 is 12 bytes for position, but this works well. You don't have to worry about calculating exactly what the offset is for the color. Once we've done that, then we can create the input layout, which we'll use later to set out to draw. So again, this brings up the possibility that you may want to have objects with different input layouts. Some of your objects may have texture maps, some of your objects may have different data in them for texture mapping, for lighting, and so on. So you could have different vertex formats for different objects in your scene. When we're done with this, the blobs here were created. Yes, the blobs here were created by these compile from files, so we're going to release them here. All right, the next step is to get the aspect ratio, and it's just the screen width over the screen height. So that's a fairly simple function there. I'll go ahead and compile this and see if we picked up any errors along the way. So far it seems okay. Something else that we're going to do in our Direct3D initialization is we need to call these functions. So this may be a good place in our initialization of Direct3D to initially set all these matrices, the worldview and projection matrix, as identity matrices, and to initialize the geometry and initialize the shaders. That might be a decent place to do that. Another thing that we're going to do is to set a raster state, and we can do that in our resize function. And again, there might be other places that we could do this okay, but and this raster descriptor is going to do a couple of things for us. One is it's going to turn off culling so that we'll be able to see the back face. The other is it's going to set the fill mode to solid, meaning that we want to see the entire polygon rendered as a point, as opposed to there's other fill modes where you can just see the vertices just as points on the screen, or you can see it as a wireframe. We may change that a little bit later, but for now we'll leave this as fill mode solid. We're going to need to define this raster state pointer. In the header file. We may want to change it later on. Or we could have different raster states created, one for solid, one for wireframe, and swap them out before we draw. The other thing we'll do now is to create our projection transformation. And so here we're going to create, using this function, matrix perspective field of view left-handed coordinate system. So this creates our perspective transformation, and our field of view is going to be 45 degrees, and here we convert that to radians. We have to pass in the aspect ratio, which we calculate as a real value of the width over the height of our screen, and we pass in values for the near and the far clipping planes. So any object that's closer than 1 unit from the screen is not going to be rendered. We'll consider that too close or behind us, so we're not going to render it. And anything that's further than 1,000 units from our virtual camera, we're not going to render that either. We'll say that's too far away. We won't worry about it. And we can change those values. We have to do something a little bit odd in that this returns, and we'll look at this a little more in detail in the math presentation, but this returns an XMM matrix, and we have to store it in this XM float 4x4, so we call this XM store float 4x4 function to put it in the right type for us. And we'll talk a little bit more about that in a future presentation. One of the next things we will do is to create an update function if we haven't already. Yeah, so we have an update function, but it doesn't do anything. So what do we want to do on our update function? Well, one possibility is to create our camera. And what I'll do is set the position of the camera at a negative value in z, so I'm kind of backing up. Remember that our triangle was in the xy plane, so it had a z value of 0. So I'm going to back the camera up to negative z and have the camera look at the origin and set the up vector equal to the y-axis. And then I call this function that gives me a look at a view transformation using a left-handed coordinate system, and I give it the position, the look, and the up direction, and this gets us the view transformation. So now when we go to render, we've got a background color and we're clearing the render target and we're clearing the back buffer and the stencil buffer. So the next steps that we want to do is to set the input layout, which tells DirectX, okay, the data you're about to receive has position and color in it, and the index data you're about to receive is made up of a triangle list, which means there's 3 indices defining a single triangle. The next thing that we're going to do is to set the vertex buffer that we want to render, and in order to do that we pass in so we could have a number of vertex buffers. Here we're passing in just a single vertex buffer, pass in its address, pass in the so-called stride. So that is, how many bytes does it take for us to go from one vertex to the next? And that's simply just the stride of the vertex buffer. And we pass in the offset. Where do we want to start rendering from? Well, in our case, we want to render everything, so we'll start rendering at 0. So there's a lot of capabilities here where you could put in additional information that's skipped by having a larger stride, and you could offset and render just certain portions of the vertex buffer. In this case, we want to render all of it. The next step is to set the index buffer, and we pass in the index buffer, and we also pass in the format of the index buffer as a 32-bit unsigned integer. The next step here is to create the world matrix and combine it. So in this case, we have an identity matrix so far. We previously set this, if we find all references, we see that we set the world matrix earlier in the program to the identity matrix. And now we're getting that world matrix, we're getting the view matrix, we're getting the projection matrix. We multiply them all together to store them in this world view projection matrix. And then we do something odd where we take the transpose. So you'll have to look up linear algebra, but the transpose is kind of like reflecting that matrix about its diagonal. And the reason we do that is that our goal is to send this matrix to the shader program, and the shader program expects matrices to be in column order, and C++ stores matrices in a row order. So we have to transpose that matrix to send it to the shader program. We update the resource in the constant buffer, and we set that constant buffer for the vertex shader. So we're setting that constant buffer for the vertex shader. So in our code, we have a constant buffer that's defined as a 4x4 float, and it is the world view and projection transform. We'll discuss this code a little bit more later, but I wanted to show you where this world view projection matrix was going. The next step is to actually draw. So we're going to draw an indexed primitive, and the index count is 3. That's the number of indices in our triangle, starting at location 0 and a base vertex location of 0. So we're starting at the beginning. So when we compile and run this, if everything works appropriately, we get a single triangle. And so you can see that we've got a single triangle, and it was red. If we go back and change one or more of those vertices, maybe change this one to a yellow color, maybe change this one to a purple color, then when we draw our triangle, you see that the vertex at 0, 0, 0 is now yellow, and the vertex at 10, 0, 0 is kind of a purple color, and then the vertex at 10, 10 is still red. So what I'm going to do is end the presentation here. There is more code for us to go over, but we'll do a part 2. And so we'll end the presentation here at drawing just a single triangle, and in part 2 we'll look at the shader code in more detail, and we will look at cleaning up these DirectX objects and possibly even putting in some simple motion with camera movement or changes in the world, the world transformation. So stay tuned for part 2 in another presentation.